All right, this video goes with 8.4a, Intro to Graphing Root Functions. So this is just a basic introduction to graphing cubed roots and square roots. We're going to start with the square root function, y equals the square root of x. So this is the parent function for square root. And I'm going to start with just making an xy table. Now you have to consider y equals the square root of x. Since you're taking the square root, we can't have any negatives under there because we're only dealing with the real number plane here. So the lowest value for x that you can plug in would be 0. The next values I'm going to choose ones that are square roots so that I don't end up with decimals. So I'm going to choose 1, 4, and 9. So then when I do my output for y, it'll be the square root of x. Square root of 0 is 0. Square root of 1 is 1. Square root of 4 is 2. Square root of 9 is 3. And then if I graph that, you can get an idea of what the square root function looks like. So 0, 0, 1, 1, 4, 2, and 9, 3. And then it's going to look like that. So the square root function, if you remember, is actually the inverse of the squared function. So if you switch the x and y and solve for y, we get the inverse function. So the domain and range switch. So that's why it kind of looks like a parabola, except for it's only the 1/2 of it because the domain has been restricted. For the square root function, for a parabola, it's all real numbers. You can plug in any number, any real number, and square it. But for the square root, you can only square root all x values that are greater than or equal to 0. Which means that, remember, your domain is your input, your x's, and your range is your output. So then all your outputs are going to be y values that are greater than or equal to 0. Okay. So here's another square root function, but this time we have a leading coefficient of 3. So we have an a value of 3. And if you remember, the a value affects, like on a parabola, it affects which way it opens, and it also affects the vertical stretch or shrink, whether it's wide or narrow. Kind of the same idea here. So to graph this, I'm going to make an xy table again, but I'm going to have a third column for ay. And a is going to be 3. That's your leading coefficient. So I'm going to choose the values 0, 1, 4, and 9. You really could pick 0, 1, 2, 3. But if you chose the value 2, then the square root of 2 is like 1.7. It's irrational. So I like to stick with the perfect squares. And then y column is going to be the square root of those. So 0, 1, 2, 3. And then for the third column, you take the middle column times your a values. So all of those middle numbers times 3. 0, 3, 6, and 9. Then when you graph it, you graph the first and last column. So it looks like this. 0, 0, 1, 3, 4, oops, trying to count here. 6, and 9, 9. So you can see how the a value of 3, if you compare it to the last one, the 3 has significantly stretched the graph. So it's a vertical stretch there compared to the parent function. It's much more wide, essentially, if you're thinking about the parabola opening to the right here. But it's a square root function. So the domain, although we've stretched it vertically, it's still all x is greater than or equal to 0. The range is all y is greater than or equal to 0. Cube root. So this is the parent function for the cubed root. Y equals the cubed root of x. I'm going to start again by making an XY table. This time when I pick perfect, I'm going to pick perfect cubes to plug in for X. And I can pick negative numbers because if I remember that like -2 cubed is -8. And so I can take the cubed root. Excuse me. So since you can take the cubed root of -8 and get -2, there isn't a domain restriction on the cubed root like there is a square root, because you can cube root negative numbers and positive numbers. I am going to pick my x's strategically, though. I like to pick perfect cubes. So like -8, -1, 0, 1, 8. And that's so that when I take the cubed root, I get whole number values, integers, instead of decimals or irrational numbers. So cubed root of -8 is -2. Cubed root of -1 is -1. Cubed root of 0 is 0. Cubed root of 1 is 1. Cubed root of 8 is 2. So graphing that, -8, -2, -1, -1, 0, 0, 1, 1, and 8, 2. So connecting that from left to right, it will look like that. And if you remember, y equals x cubed looked something like this when we graphed cubed functions. You will see the resemblance in the inverse function, the cubed root. It's reflected over that diagonal line y equals x. Since there's no restrictions and you can take the cubed root of all real numbers, your domain is all real numbers. And I like to write that as x is an element of the real numbers. I think my pencil just died here, but give it a second. So, let's see. X is an element of the real numbers. And then, since there's no restriction on what numbers you can plug in, your y values, your range will be all real numbers as well. So my range will be y values that are all real numbers. Did this to me last time as well. Y values, all real numbers. Okay, so that's the parent function for cubed. All right, the next one. Notice you have the -1/2 out front. So I'm going to do this with an XY table, but this time I'm going to include the third column because it's -1/2 is your A. So for the cubed root, I pick perfect cubes, -8, -1, 0, 1, 8. So the middle column is the cubed root of those values, so -2, -1, 0, 1, 2. And then the third column, you take the middle column times the half on each one. So I'd get 1, 1/2, 0, -1/2, and -1. And then graph the first and last column. So -8, +1, -1/2, 0, 0, 1, -1/2, and 8, -1. So you'll see, let me shut that off. If I zoom in here, connect this. If you compare it to the last one that we did, you'll see that the 1/2 was a vertical shrink. The graph kind of looks more narrow if you're looking at it horizontally, like it's closer together. Another thing you might notice is that it is reflected over the x-axis. So this one was up here was like this, and this one down here is reversed. So it's kind of similar to if you have y equals positive x squared, parabola opens up. If you have y equals negative x squared, the parabola opens down. Remember, that's the a value that is controlling that reflection over the x-axis. So the negative reflects it, and then the 1/2 is a vertical shrink to the graph. So that's how that 1/2 changes it from the parent function. The domain is still all real numbers for x's, and the range is still all real numbers for y's in this particular example. All right, thanks for watching.